Hey everyone, welcome back to the channel Code with AKJ. Today is day 35 of solving LeetCode 75 challenge series. So in this video, we'll be solving a really interesting binary tree problem from binary tree DFS, that is count good nodes in binary tree. So this problem is not only common in interviews but also teaches a valuable lesson about carrying state during recursion. So we'll first understand the problem, then move from a brute force approach to an optimal DFS solution. And yes, don't forget to subscribe to the channel for daily TSA problems and optimized solution. So let's get started. So the problem statement says, given a binary tree root, a node x in the tree is named good if in the path from root to x there are no nodes with a value greater than x. Return the number of good nodes in the binary tree. So we are given the root of a binary tree. A node x is called good if in the path from the root to x no node has a value greater than x, and we need to count all such good nodes in the binary tree. So let's understand with these two examples. Example 1, we have values 3, 1, 4, 3, null 1 and 5. So in this given binary tree, the good nodes are 3, 3, 4 and 5. Let's understand why these nodes are good and why these two nodes are not good. So in this given binary tree, so for every binary tree, the root node is always counted as a good node, as we don't have any ancestor or the parent node to compare it to. Next, if we consider the node 1, so the path from the root to this current node has two number of nodes, that is 3 and 1 itself. So to consider 1 as a good node, we need to find a node whose value is greater than the current node. So the current node value is 1 and we have a node value which has a value greater than the current node. So that's why we cannot consider this one as a good node. So coming to this node 3, the current node 3. So the path from root to this current node has two number of nodes, that is 3 and 1. So if any values whose value is less than or equal to the current node, we can consider it as a good node. So from this particular root to this current node path, we have a node whose value is equal to the current node, so we can consider this node as a good node. So coming to this current node 4, path from root to this current node 4 has two number of nodes, that is 3 and 4, and there are no nodes whose value is greater than the current node, so we can consider this node as a good node. And coming to the node 1, the path from root to this current node has two number of nodes, that is 3 and 4. These two nodes have values greater than 1, so we cannot consider this node as a good node. Coming to the node 5, the path from root to this current node 5 has two values and there are no nodes whose value is greater than 5, so we can consider this node as a good node. So since we have checked for each and every node the path from the root to that particular current node, we can see that there are 4 nodes which are good nodes. So the count of good nodes for this given binary tree would be 4. So we'll return 4 as an answer. So let's understand the concept of good nodes with the help of this example as well. So the root of the binary tree is always a good node. So 3 is a good node. So if you consider this current node 3, so as per the definition of good node, in the path from root to the particular current node x, there should be no nodes whose value should be greater than the current node. But here, since the node values are same, we can consider this as a good node. And coming to the node 4 here, the path from root to the current node 4, there are two number of nodes whose values are not greater than 4, so we can consider this node as a good node. And coming to the node 2 here, the path from root to the current node has values 3, 3 and 2 itself. So we have nodes whose value is greater than the current node, so we cannot consider this current node as a good node. So for this given binary tree, there are 3 good nodes, so the count would be 3. So for this case, we'll return 3 as an answer. So this was the problem statement about counting good nodes. So let's get started with a brute force approach. So let's think simply first. So for each node, we want to know if all the nodes from the root to this node have values less than or equal to it. That is all about finding the good nodes. So the definition of the good node is nothing but if in path from root to the current node x, no node should be present whose value is greater than current node value, or there should be nodes whose value should be less than or equal to the current node value. So in the brute force approach, for each node, we'll first find the path from the root to the node, and then we'll check if any value in the path is greater than the current node's value. So if not, we'll count it as a good node, and finally we'll return the count of our good node. So to implement this, we can use a recursive DFS where we pass a vector representing the path from the root to the current node. So let's understand our brute force approach with the help of this given binary tree. So we'll solve this particular binary tree and we'll find the number of good nodes using our brute force approach. So with the help of this table, we'll try to find the path for each and every node from root, and we'll check whether the given current node is a good node or not. So since root of every binary tree is a good node, 3 is considered as a good node. So let's go to the node 1. So the current node is 1. The path from root to the current node has values 3, and we'll find the maximum value in that given path, that is 3, and current node value is 1. So as per the definition of the good node, there should be no nodes whose value should be greater than the current node value. So since the max value in that path is greater than the current node value, which is 1, so we cannot consider this current node as a good node. So we'll move on to the next node, that is 3. So the current node is 3. The path contains values 3 and 1. The maximum value of this path is 3. Current node value is 3. So since the values are same, we can consider this as a good node. So coming to the next node, 4. So the path contains 3. So the maximum value in this given path is 3 and the current node value is 4. So there are no nodes in this path whose value is greater than the current node, so we can consider this node as a good node. And coming to the next node 1, the path contains values 3 and 4. The maximum value in this given path is 4 and the current value is 1. So there are nodes whose value is greater than the current node, so we cannot consider this current node as a good node. So it is not a good node. And coming to the final node 5, the path contains values 3 and 4. The maximum value is 4, current node value is 5. So there are no nodes whose values is greater than current node, so we can consider this node as a good node. So this should be considered as a good node. So if we check the number of good nodes, so there are 1, 2, 3 and 4. So there are 4 good nodes in this given binary tree. So we'll take a variable count which would be initially 0, and whenever we find a good node, we'll increment this count variable. And finally, after finishing our process for each and every node with the help of recursion, and since we are storing all the values in the path, we'll also use a vector or list. We will finally return our count of good nodes in the given binary tree. So for this given binary tree, the count would be 4. So the time complexity of this approach would be O of n cross h, where n is the total number of nodes and h is the height of the tree. So for each node, we may iterate the full path, that is up to the height of h. So the overall time complexity would be O of n cross h. And coming to the space complexity, the space complexity would be O of h, that is height of the tree, that is for recursion, and O of h for the path vector. So let's code this approach and let's submit. So here's the code for our brute force approach. Here I have taken the path vector which will store the values from root to the current node. I've called the DFS function where I'll pass the root of our tree and the vector of path. I've taken the count variable which is globally declared, which would be initially 0. So the DFS function goes like this. So if we found a node which is null, we'll return from it. First we'll check if the node is good or not. So we'll take a bool variable is good, which would be initially true, as the root of the tree is true initially. We'll check in the path if a value is greater than the current node's value. So if it is, then we'll mark our is good variable from true to false and we'll break from the vector. And we'll check the is good variable. If it is true, then we'll increment our count variable. If it is false, we'll move on to the next node. And coming to the recursive part, we'll first initially push the current node into our vector and we'll make 2 recursive calls that will call the left subtree and then right subtree, and we'll again for every call we'll check this particular condition in the path. After processing a particular node, we'll remove the values from the path for next node's processing. So finally we'll backtrack the values from the vector of path using popback function. So in this way, with the help of vector and recursive calls, we'll be able to store the node values for each and every node and check whether the node values has the value greater than the current node value. So the issues with our brute force approach is we are repeatedly scanning the entire path for each node and which is inefficient especially for larger trees, which is up to 10 power 5. So since our brute force approach has some issues where we are repeatedly scanning the entire path for each node, so in our optimal approach, so instead of storing the entire path, we'll just keep track of the maximum value we have seen so far during traversal. So if the current node's value is greater than equal to the maximum value so far, it's a good node. So the idea here is we'll start DFS from root. So at each node we'll compare the value with the current path max. So if it is greater or equal, we'll count it as a good node and we'll recursively call for its children by passing the updated max. So by doing this, we'll reduce unnecessary work and we'll still check the same condition. So let's understand how our optimal approach works by dry running this given binary tree. So we'll start our DFS call from the root by sending the maximum value, which is the root value itself. The first part here is the node value and second part is the maximum value we have seen so far during traversal. So this call gives a recursive call to its left and to its right. So for this call, the node is 1 and the maximum value is 3. So since the maximum value is greater than the current node, we'll not count this node as a good node, and it gives us call to its left value by sending the max value we have seen so far. So the max value we have seen so far here is 3. So this node will get the maximum value as 3 and current node is 3. So since they both are same, we'll consider this as a good node. So this call gives a right call to the 4, sending its maximum value, that is 3 here. So the maximum value here is still is less than or equal to the current node, so we can consider this node as a good node. It gives a call to its left child and right child. So the left child gets a maximum value as 4. Current node value 1 will get the maximum value 4 we have seen so far during this traversal. And since the maximum value is greater than the current node, we won't consider this as a good node. And coming to the child 5, the maximum value here is 4, and since it is less than or equal to the current node 5, we can consider this node as a good node. So in this way, with the help of recursive calls and by sending the maximum value we have seen so far during the traversal, we can reduce unnecessary work, that is repeatedly scanning the entire path for each node. So it is also efficient for the larger trees, that is up to 10 power 5 nodes. So the time complexity of this approach would be O of n, as we are visiting each node once, and the space complexity of this approach would be O of h, that is the height of the tree, that is for recursive stack. So this is the most optimal solution possible for this problem. So let's get started with the code and let's submit. So let's start writing our code. So the base case here would be if root is null, we'll return 0. We'll send a DFS call sending the root value and the current max value, which is root val, and we'll return count variable. So we are declaring the count variable globally, which would be initially 0. So let's start writing our DFS function, which would take a node and max so far value. So again, the base case would be if node is null, we'll return from there. We'll check if node value is greater than or equal to the max so far, which means it is a good node. So we'll increment our count variable. We'll update our max so far for every traversal equals max of max so far value with the current node value. So we'll give the recursive call to the node left by sending the max so far value, and we are sending the recursive call to the node right by sending the max so far value. So in this way our optimal solution works. So the time complexity here will be O of n, as we are visiting each and every node only once, and the space complexity here will be O of h, that is height of the tree, as we are storing each and every node in a recursive stack, which would be O of height. So let's run this code. It's working, so let's submit. As you can see, it gives us a successful submission, and it is the most optimal solution for this problem, even efficient for the larger trees up to 10 power 5 number of nodes. So that's how we solve the count good nodes in a binary tree problem, starting from brute force and optimizing it using DFS and max tracking. So if this video helped you understand the concept, smash that like button, drop a comment, and most importantly, subscribe to the channel so you don't miss out on more coding content. So thanks for watching, and I'll see you in the next one.